Alright, so chapter 2, we're going to look at some graphical summaries that we can use for our data. Alright, so first thing we want to look at is what we call a frequency distribution. A frequency is just the number of times something happens. So like I can look around the room and I can say how many people have brown hair, black hair, blue hair, green hair, and I would just tally up how many people will fall in that category. Well, that count that I'm tallying is my frequency, and a frequency distribution is simply the table that I put those counts into. We also have what we call a relative frequency distribution, where we change it to percents. So again, a frequency distribution, or a frequency, is the actual count itself, whereas your relative frequency is to the percent. So I would just take my frequency, divide it out by all the total, or the sum of the frequencies, and that would give me my relative frequency, which is the percent of people who have, for example, brown hair, blue hair, black hair, green hair. So one more time, the difference. Frequency is your counts. Relative frequency is your percents. So here's an example of just some data on types of computers sold. We have desktop, laptops, notebooks, and tablets. And so from this data, I just simply tallied up how many desktops we had, laptops, notebooks, and tablets we had. And so I got 11, 23, 9, and 7. And so that's my frequency, because that's the actual counts of how many I have. Then to get my relative frequency, I can get the total of all of this, which looks like, I don't know, 30, 40, 50 total computers. And I take, for instance, for desktop, I would take the 11 divided by the total 50 to get a relative frequency of 0.22, or 22% of the data was desktop. Now, with those frequencies and relative frequencies, we can construct graphs to help us better visualize the information. The first type of graph that I want to talk about is called a bar graph. Many of you guys have seen those before. A bar graph is just a graph with rectangles that represent the height of whatever the data tells us. So whether it's a frequency or a relative frequency, that height tells us, how much of the particular variable there is. Now, the key with bar graphs is to make sure that you have an equal width of a bar. You don't want one bar to be fat and one bar to be skinny. You want the bars to be the same width. Also, you do not want the bars to touch. The bars cannot touch. That's not a bar graph. When the bars touch, we call that a histogram, and it's a little bit different. So you want to make sure when you're doing a bar graph, you're just keeping your bars separated to actually see the frequency or relative frequency for that particular category. Now, below I have steps for constructing the bar graph. I'm not going to go into that in detail because we're actually going to construct one in class when we meet on Tuesday. In addition to bar graphs, we have what we call Pareto Charts, or Pareto Charts, pronounced differently depending on who says it. These charts are the same exact thing as a bar graph. The only difference is you put it in order from largest to smallest. So the largest bar would be to the left, and the smallest bar would be to the right. These graphs are very helpful when you're trying to see like which one happened the most and which one happened the least. You don't have to like scan the whole bar or the whole graph. You could just look at the very beginning or the very end of the graph. So again, a Pareto chart or Pareto chart is the same exact thing as a bar graph, except for that it's put in order, greatest to least. We also have what we call a side-by-side bar graph. A side-by-side bar graph compares two things. For instance, if I had like a two-way table where I was looking at the types of computers bought, and then I was also looking at whether the person was a male or a female. Well, I would do a side-by-side bar graph, so I could say like desktops for males, desktops for females, laptops for males, laptops for females. And in that case, those side-by-side bars actually do touch. So the two that you're comparing, they can touch. But between the actual variables themselves, like desktop, laptop, whatever, those wouldn't touch at all. And again, that's called a side-by-side bar graph. Next, we have a pie chart, which we don't use that often because it's very, very hard to make by hand. But a pie chart is very similar to a bar graph in that it shows the relative frequency of your data. Your pie chart is basically a circle. You divide it into sectors, and each sector represents the relative size of whatever the data represented for that category. All right, so here's like an example of a pie graph. Here we see like laptops was the highest, had the highest frequency and the highest relative frequency. So that's why this sector of this pie chart is largest. Now again, it takes a little bit of work to actually construct the pie graph. You'd actually have to multiply your value by 360 to figure out the area of the sector and then actually draw it out accurately. But again, we usually use technology to construct them if we had to make them. Bar graphs are a lot easier to make by hand versus a pie chart. We usually use technology. Now we can also have frequency distributions and relative frequency distributions for quantitative data. All this stuff that we were just looking at was for qualitative. We could also do the same thing for quantitative data. So we can have frequency distribution, we can also have a relative frequency distribution, but this time we're looking at numeric values. So for example, here's my data set, just some data, some decimals. This could be, I don't know, time it takes you to brush your teeth. I don't know what this is, but just some data. And so what I would do to create my frequency distribution is I would create these classes. In other words, I'm going to create a range. Like everything between 0 and 0.99 would go in a class. Everything between 1 and 1.99 would go in a class. Everything between 2 and 2.99 and so on would go in a class. And then I would just tally up how many numbers actually fell in that range. And again, that's just a frequency distribution if the data was quantitative. Because all the values are pretty much different. They're not in categories. We create categories for them. So basically what you're going to do when you're creating your frequency distribution is you're going to have a lower class limit and an upper class limit. The lower class limit is the smallest value that can appear in the class, where the upper class limit is the largest value that can appear in a class. And then the width of your frequency distribution is the difference between consecutive lower limits. So from one lower limit to the next, that's the actual width of your class. All right, so for here, our lower class limits, same example, our lower class limits would be like 0, 1, 2, 3. Those are the lower numbers in each class. And our upper class limit is, our limits are 0.99, 1.99, 2.99, and so on and so forth. The width is the difference between consecutive lower class limits. So the width would be from 0 to 1, that width, that distance, that difference is 1. So the width of our class is 1. All right, some requirements that you need to know when you're choosing your classes. Every observation must fall into the class, so you can't leave an observation out. Your classes cannot overlap, and they have to be the same width. So if you count by ones, everything has to be ones. There's no gap between classes. Even if there's no observation in that class, you still have to include it, and you just would say 0. All right, so if you're constructing your own frequency distribution, and again, we're going to do this in class, but I can't find the answer to the question I heard. Sorry, that was my Alexa. But if we're going to do this in class, but just to give you an overview of what I'm talking about. So what you're going to do is you're going to choose your class width, which again, that's kind of up to you. It's not like a set width. You do want to have enough bars to make your graph look good or your data look good, but you don't want to have too many bars where it's kind of confusing. There's not a lot in each class. So you choose your own class width, you'll choose your lower class limit, and then you'll choose the lower class limit for the next set. Once you have those, based off of your width, so once you get that first limit, then you add the width to it to get the next width, the next lower class limit. And you keep doing that until you're all done, until every single observation falls into a class. From there, you just have your frequency distribution. So how do you figure out the width? Well, again, it's totally up to you how many classes you want. But again, you want to make sure you have enough classes to kind of make it look good, but not too many to where it's like cluttered and too much data. It's not purposeful. So what you do is you decide on how many classes you want to have, and then you take your largest value and your smallest value, subtract the 2, and then divide by the number of classes. Now you always want to round that number to something convenient. For instance, if you got something like 1.6, you might decide to do a class width of 2. Or if you divided and you got like 1 or 2.89, something like that, maybe your class width would be 3, just to make it nice and easy for the reader or for your audience. Now with that, once you create your frequency distributions or relative frequency distributions, again, you always kind of want to show it in a graph. For quantitative data, we have several different graphs other than like the bar graph and stuff like that. The bar graph, the pie chart, the Pareto, those are all for qualitative. But for quantitative, you have a whole different set of graphs. And so the first one is what we call a histogram. And it's very similar to a bar graph, except for now your bars actually do touch. So again, in your histogram, your bars do touch. And so each bar of the histogram represents that class width, that width that you have. So you have a bunch of values between two numbers, and then you draw a bar for how many values you have between those two numbers. And again, we'll draw one out in class. I'll show you guys how to do it exactly. But again, it's the same thing as your bar graph. It's just a graph where the bars actually do touch, and they represent, values within a particular class. All right, so this is what our histograms look like, and we have kind of different shapes of histograms. The first one is skewed left, and we say it's skewed left because the left side is kind of lower than the right side. The second one in the middle is what we call symmetric, and your symmetric graph is pretty much even on both sides, left and right. Now again, it doesn't have to be perfect. It's rare that you have actual perfect exact data, but it's roughly symmetric, we like to say. And then over here we have skewed right, and that's because the right hand side is kind of skewed down more than the left. The way that I remember skewed right and skewed left is I look at my feet. For skewed left, it looks like my left foot. My big toe is to the right, my little toe is to the left. And for skewed right, it looks like my right foot, where my big toe is to the left and my little toe is to the right. I don't know if that helps. Hopefully it does. All right, we also can describe our histograms by its modes. And so we have two types of modes. The first one we have bimodal, where you have two modes. And what I mean by modes are like the actual humps of the graph. So like I have a hump here and I have a hump here. So because I have two humps, we call this bimodal, two modes. Whereas here I only have one major hump in my data, and so we call that unimodal. All right, another type of graph is our stem and leaf plots. Stem and leaf plots are kind of fun to make. Basically, you're taking your data and you're separating it out. So you're saying, okay, well, the first on the left-hand side of my stem leaf plot, I'm gonna put all of my data values on the right-hand side. I'm gonna leave one value out, and doing that, you can actually see whether or not your data is skewed left, skewed right, or symmetric. Now, the key to this is that it's only good to do with small data sets. If you had a data set of like 200 people or something like that, this would be unrealistic to do. But if your data set's kind of small, it's a lot easier just to do a stem and leaf plot than it is to do a histogram. Now, we could also have what we call a split stem plot, where instead of counting like 0, 1, 2, 3, 4, 5, we count 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. The purpose of a splitting limb or splitting stem plot is that it helps you so that you can see the data better, especially when the data is clustered in a small amount. We also have a back-to-back stem plot that you'd use when you're comparing two sets of data. So like males and females, you want to look at it on one chart, you would create a back-to-back stem plot. And again, we'll look at these in class. Next, we have a dot plot, which again is just like your bar graph, except for you're using dots. It gives you the rough shape of your distribution, and again, it's useful when the data set is small. And lastly, we're not going to spend much time on this in this class, but we have a time series plot, which is useful when the data is measured at different points in time. So here's an example of a time series plot. We're looking from 2000 to 2009, and we're looking at the average Dow Jones. So that's what our time series plot looks like. And again, we'll do examples of each one of these plots in class so that you have a better understanding. All right, that's it.